In this video, I want to now cover the material in Chapter 4. So we have introduced the concepts of thermodynamics, and we have looked at the very important chapter associated with the calculation or the determination of thermodynamic properties. And so we're now going to look at applying the conservation of mass and energy on a control volume analysis. So I'm going to go ahead and share my screen here. And we're going to go back to so I'm sharing the screen and I go into So in this particular chapter, as I said, we want to look at the conservation of mass as well as the conservation of energy equation. And one of the first things that we identify is that if we have one-dimensional flow through a duct of a given area, we can represent the mass flow rate by rho AV, density times area times velocity. And since density is just 1 over the specific volume, you'll see it in this particular form here. Area is the cross-sectional, the one-dimensional cross-sectional area for which the velocity is passing, the fluid is passing through that area with a constant velocity v. And again, specific volume v is just how many cubic meters per kilogram does the fluid possess. And again, that's just the inverse density. So the conservation of mass basically just says that if we look at a control volume, the amount of mass that's building up in the control volume on a time basis is just simply related to the mass flow rates coming in and the mass flow rates going out. And so it's just a accounting process. If the incoming is much higher than the outgoing, then we see that there's a positive rise in the mass within the control volume. If we assume we have steady state, then this derivative, this mass in the control volume, remains constant, and we then can say that everything that goes in has to be equal to everything that goes out. And so that is our steady state process. Okay. Now, when we apply the conservation of energy to the fluid going through a control volume, we arrive at the energy rate balance, where if we assume non-steady, the left-hand side just is equal to the time rate of change of the energy, the stored energy within the control volume, and that is related to how much heat transfer, the rate that heat transfer is going into the control volume, and the amount of work that the control volume is doing to the environment. Again, there's our negative sign because of the definition of the heat transfer as positive going in and the work as positive leaving the system. Because there's a fluid that's passing through, coming in to the entrances and going out the exits with certain mass flow rates, we recognize that those fluids are bringing with them energy in the form of internal energy and flow work. Recall that enthalpy was just internal energy plus PV, which is a flow work term. And so think of this enthalpy as just the energy possessed by the flow as it's moving in. And that flow also has a kinetic energy and a potential energy associated with it. So the energy that's actually passing into the system is given by this expression. Each of these terms are on a specific basis. They are on kilojoules per kilogram. One has to be careful when one has the velocity squared over 2. Velocity squared over 2 is just meters squared per second squared. That's not the same unit as kilojoules per kilogram unless you convert it and add the factor of 1,000. And so a lot of times you'll see this equation with 2,000 as the denominator here, because in order to go from meters per second squared to kilojoules per kilogram, one has to divide by 1,000. Likewise for the potential term. And the same thing holds for the mass that is leaving at each of the exits. They possess a certain amount of enthalpy as well as kinetic and potential energy. If we again assume steady state, our left-hand side becomes 0, and then we have this heat transfer in, the work that's being delivered out of the system being related to multiple inlets and multiple exits. What usually happens is our systems are typically just a one entrance and one exit, one inlet and one exit. And so these summations just become over 1. And we also recognize that if it's steady state, that the conservation of mass would tell us that the m dots are the same, and so we can bring those out of the equation. So these two terms then combine together to give us a difference in the enthalpy, where 1 and 2 are just the inlet and the exit. Our kinetic energy change again between 1 and 2, the inlet and the exit, as well as our potential in our inlet and our exit 1 and 2. By dividing this m dot through each of the terms, we then have a form of the equation that is in specific energy, the change in the enthalpy in kilojoule per kilogram, plus the change in the velocities, the kinetic energy terms, plus the change in the potential energy terms, then give rise are due to heat transfers and works. And these terms here, since a Q dot is really a kilojoules per second and an m dot is kilograms per second, these terms here are just heat transfer per mass, work per mass. And so this equation here is the steady flow, single inlet, single outlet, control volume, first law of thermodynamics on a per mass basis. And this is on a, if you want to think of it, on a power basis, a rate basis. Each different type of device has differences associated with it. If it's a nozzle, if we're looking at a nozzle, what happens is kinetic energy is an important term, because the purpose of a nozzle or a diffuser is to either speed up or to slow down the flow. And so one would have to retain this term here. If one was dealing with a pump, one of the purpose of a pump is to raise the fluid up to a higher potential energy level. And so if you had a pump, this term here may be of importance. And so, but most devices that we're going to be looking at is just taking a fluid and having that fluid change its enthalpy value by either adding heat, taking away heat, adding work, doing work, changing the velocity, or changing the potential energy. So it's really just an accounting basis. One of the things that is discussed in this chapter is what's referred to as a throttling process, a very simple process where there's no heat transfer occurring, there's no work occurring, there is no velocity, perceivable velocity change, and no position change. And because of that, what happens is enthalpy remains constant for the steady process. And so that's just the ramification of a generalized one inlet, one exit control volume at steady state, wherein a throttling process occurs. And typically that throttling process is driven by the fact that pressure is decreasing. You know, you have a high pressure and you have a valve on the tank of that high pressure. You open up that valve, the fluid is then exposed to a lower pressure and it rushes out of the throttling valve or out of the valve in such a fashion that enthalpy during that process remains constant. Okay, so that's chapter 4. Very briefly, chapter 5 gets into the definition and the discussion of the second law. And so in this particular chapter, the concept of the second law, the statement of the second law is given, a discussion about what's the difference between internal and external irreversibilities is given. What is an irreversible process? What corresponds to irreversibility in a system? Various corollaries to the second law, the Carnot corollaries, the Clausius inequality, all associated with the second law. And so I would recommend that you, if you are weak on the second law, that you might want to go back and reread through this particular conceptual channel and chapter, and understand the processes. Will be introducing entropy next time, which is a outgrowth from the second law, and we will be saying things like when we have irreversible processes occurring, we have a generation of entropy. And so we will tie that, those irreversible processes that occur because of the second law of thermodynamics to the magnitude or the production of entropy in a system itself. But what this chapter does do is introduces what is referred to as the Carnot efficiency of various types of devices that undergo certain cycles. And so what we find is the one form of the second law is that is shown here, is that this work of the cycle is less than or equal to 0. And what that implies is if it's the less than term, we basically say that internal irreversibilities are present. If the work of the cycle is equal to 0, then in essence it's saying that there are no internal irreversibilities occurring for a cycle communicating with a single reservoir. When we talk about power cycles, okay, we can define the efficiency of a power cycle. The maximum thermodynamic efficiency of a power cycle operating between two temperature reservoirs, and those two temperature reservoirs is where energy is being supplied from to the cycle and away from the cycle. So if you have a power cycle operating between a high temperature and a low temperature, the high temperature is where the heat is coming in, and the low temperature is where heat is being rejected. And we know that the difference between those two heats is related to the work of the cycle. And so that's this work of the cycle. And if everything is done in a perfect fashion, where the work of the cycle is equal to zero, then we can say that the system is operating at its maximum thermodynamic efficiency. And it turns out that that is directly related to the temperatures of those two reservoirs. We also spoke earlier about refrigeration and heat pump cycles, and the same type of analysis can be discussed in those types of cycles. Once again, the high temperature reservoir is the reservoir that's accepting the heat transfer from the working fluid, and the low temperature reservoir is the reservoir that is supplying heat to the working fluid. So we're trying to maintain the temperature T sub C in a refrigerator by taking energy out of it into the refrigeration cycle, into the working fluid, and we're expelling it to the high temperature reservoir associated with the cycle. And we find that the best efficiency, the best coefficient performance is directly related to those temperatures associated with the reservoirs. Likewise, the heat pump is very similar. We are looking at the amount of heat that can be rejected into the high temperature reservoir as we pull that heat from the lower temperature reservoir. And the maximum coefficient of performance for a heat pump is given here. What we'll find later is that real refrigerators and real heat pumps will operate at values lower than this maximum value. So the Carnot is the best we can obtain in operating cycles between two thermodynamic reservoirs. Another concept that's discussed in this particular chapter deals with entropy, which is discussed in chapter 6. And if one were to look at all of the heat transfers that are going in or coming out of a cycle, and those heat transfers occur at temperatures at the boundary of that particular process, if one performs the cyclic integral of the heat leaving at a given temperature at a point on the boundary of the system and integrate that over the entire cycle, one then arrives at a number that is a negative value. Sigma cycle is defined as the production of entropy, a magnitude. That the sigma is a positive number. Negative means it's negative that positive number. So Clausius inequality basically tells us that this integral is equal to some value associated with the production of entropy. If the production of entropy for the entire cycle is equal to 0, then it's this term on the right hand side is equal to 0, and we have a reversible cycle occurring. So no internal irreversibilities. Okay, so we're going to stop here. The next and last video will correspond to chapter 6, which gets into the meat of the matter in defining the entropy and how we go about determining the change of entropy between two equilibrium states, and how the second law basically defines that entropy, and the second law along with the first law then allows us to to analyze our cycles.